Let's look at regression. Linear regression is used to look at things over time. When we're doing statistical analysis, if you have something that is done over a timeline, you need to use linear regression. You can see what sort of trend you're getting at. In general, regression is the statistical model for determining the relationship between a dependent variable, and the dependent variable is the one that you get an output from, and one or more independent variable. The independent variable is the one that we vary. If you're looking at the growth of the plant based on the amount of nitrogen applied, the growth of the plant is the dependent variable, and the nitrogen is the independent variable. We expect as you put nitrogen down that you will get an increase in plant growth due to the amount of nitrogen applied. Therefore, as you put the nitrogen down, which is your independent variable, that is going to cause the growth of the plant to increase. That is what we would expect. You start out in the springtime. You're going to have X amount of biomass. As the growing season increases over time, you expect that biomass to increase. You're looking at your independent variable because you can't control the growing season. The dependent variable that comes out of that is as more time goes by, you get more biomass. We look at cause and effect. Regression analysis is used to estimate relationships between a dependent variable and one or more independent variables. Independent variables, like we said, are things that we change. Time is one because we have an increasing growth over time. We may look at concentration of something in the soil and therefore many other sorts of things. We use regression to look at reactions over time or over a gradient. I keep on stressing time because when you're doing this, you're looking at a control. Examples of regression include the amount of nitrogen supplied on the concentration of that nutrient in the organism. If we apply different levels of nitrogen, we can then see the amount of nitrogen that the plant picks up, and that would give us a regression model. We could look at the accumulation of biomass in plants over time. We could look on the effect of salt on the desiccation of tissues over time. Salt is one of the major preservatives that is used to extend the life of food. If you add salt, you can desiccate material. If you add salt to a plant, you could look at how much it suppresses growth over a time span. Modeling. How do we model linear regression? We're going to look at the mathematical model where y equals a plus bx. Y is the dependent variable. A is the calculated effect when x equals 0. B is the slope or the rate of change of y relative to x. We also calculate error based on the goodness of fit of the data. What is goodness of fit of the data? Whenever we have something going on, we're always looking at how well does the data fit our particular model. Remember, we're trying to make a linear model out of something. Sometimes linear fits well, sometimes they're not the best. The error becomes too great. When we calculate this, it tells us that data fits the model. The calculations are not difficult. There's some information that we have to have. First are the values of x that were used to determine the y. The more values that you have, the better the fit that you can obtain. We need the values of y that were determined at each x. We're varying x and trying to figure out what happened with y. This data set was from repetitions of a test. Concentrations of salt at 0, 1, 2, 3, 4, or 5 grams of salt in 100 mLs of water were used. We placed 6-inch long square rods of fresh potato into each sample of water. We might call them a French fry before they were cooked. We did 3 sticks per concentration. After 20 minutes, the potato sticks were removed and measured. We did this in a plant physiology class. These are the data of what we got. We have the concentration of salt that was used, the X values. We've got the length we measured, the Y values. We've got how much it was at the beginning. We've got how much it was after. We can calculate the amount of change of the initial length relative to the salt concentration. The regression model comes down to y equals a plus bx. Y is the final length of the stick. X is the concentration of salt used. A is the intercept, which in this case should be 6 centimeters because that's where we started out. Sometimes when we make this calculation, we don't come out exactly with 6. We may come out with the variation. We could force the line to go through 6, or we can actually check and see where it is to see how good it actually came out. B is the slope or change due to the concentration. This will be done using simple calculations that the spreadsheet will create. We will need to calculate the following values. N is the number of pairs of data points that we have. We need the sum of X, which is the sum of all our X values. We need the sum of Y, which is the sum of all our Y values. We need the sum of X squared. That is where you take each one of our X values, square it, and then add these values together. We need the sum of Y squared, which is the sum of each Y value squared. We need the sum of XY, which is the sum of our X values times the Y value for that X value. We can easily do this on Excel, and we've got a video to show how to do that. The link is in the video description. Let's calculate the regression for this data set. We need to calculate the following values. We need the N, which is the number of data points. In this case, it's 18. We need the sum of X. You add together all the X values, we get 45. You need the sum of Y. Adding all the Y values together, you get 103.5. You need the value of each X value squared. If we take the 0, we square it, we would get 0. The 1 squared gives us 1. We add those values together and we get 165. Then we do the same for the Y. We get the sum of the Y squared values. That gives us 595.77. Then we get the value of the XY. X times Y. We add these together. We get 253.2. We then take these values and we use them to calculate the intercept. The intercept equals, on the numerator, the sum of Y times the sum of X squared minus the sum of X times the sum of XY. In the denominator, we have the number of data points we have times the sum of the X squared values minus the sum of the X valued squared. Let's go back to our data points. Starting out of the numerator, the sum of Y equals 103.5. The sum of X squared equals 165. That value minus the sum of X, which equals 45, times the sum of XY, which equals 253.2. In the denominator, we have N, which equals 18, times the sum of the X squared values, 165, minus the sum of X, 45, squared. We substitute these values into the equation and we come up with this. Remember PEMDAS. We do parentheses first, then exponents, multiplication and division, before we do addition and subtraction. If we simplify these values, we get these values here. We then simplify those values, and you come up with this number right here. This looks like a rather large number, but it's a simple calculation using a calculator or spreadsheet. Then you calculate this out. Your intercept is 6.014. Remember, in this particular case, the intercept was supposed to be 6. This is the calculated value. This is a very good calculated value in that it is very close to the value of 6. The slope is how much angle does our particular line have. Go to our equation. The slope is the number of data points, 18, times the sum of the xy, 253.2, minus the sum of x, 45, times the sum of y, 103.5, divided by the number of data points, 18, times the sum of the x squared, 165, minus the sum of x, 45, and we square that value. We have these values in our data set. All we do is plug them in. Remember PEMDAS. We do the parentheses first, then the exponents, multiplication and division, before we do the addition and subtraction. We take these values, we substitute. We do the first calculation there. The second calculation, we've got negative 99.9 divided by 945, which gives us a slope of a negative 0.1057. What does that mean? This means that in this case, our slope is negative. As we go farther from the y-axis, the line is actually going down. This means as the concentration of salt went up, the lengths that we got went down. We can take these values and do a scatter plot. Then we can add in the equation that models this line. This allows us to observe our trend. In regression, we calculate the R-squared value. Our R-squared value gives us a goodness of fit. This calculation looks a little more complicated as it has levels of parentheses. Just pay attention, and the calculations are not difficult. It takes XY values and divides it by the X and the Y values. Again, we're going to look at these based on PEMDAS. We do parentheses first, then exponents, multiplication and division before we do the addition and subtraction. We've got different brackets and we've got different parentheses, so we take care to do them in order. In the numerator, we start out with n, 18, times the sum of xy, 253.2, minus the sum of x, 45, times the sum of y, 103.5. We take that whole value and we square it. In the denominator, we take n, 18, times the sum of x squared, 165, minus the sum of x, 45 squared. We're going to multiply that. Notice the brackets again. N, 18 times the sum of y squared, 595.77, minus the sum of y, 103.5 squared. These are rather simple calculations that you can do with a calculator on a spreadsheet. First, solve the first set of multiplications within each parentheses. We get these values. Then we do the subtractions, and we get these values. We square the numerator, and we multiply the denominator, and we get these values. These values gives us an R-squared value of 0.9096. So an R-squared value of 0.9096 is a very good goodness of fit. We're going to take this to an R-squared table, which will tell us our significance. This will tell us our goodness of fit. I can tell you right now, 0.9096 is looking good. Here is our scatter plot again with the equation as the final product. Calculating regression may look like a difficult task, but it is fairly simple math, especially when you use tools at your disposal, such as spreadsheets or scientific calculators.